Hello, everyone. So now we are going to move to the next topic, and that is about beam elements. So in this lecture, what we're going to do is we're going to talk about the beam element stiffness matrix, and then how to analyze structures that are composed of beams. And I'm pretty sure that you must have analyzed like structures made up of beam elements, but this is a different way of doing things. And it's a very interesting way of analyzing the structure. So all the ideas actually that you have learned for trusses applies to the beams also. But what we have to do is we have to just now in this case find the right stiffness matrix for the beam element so we can use it. Um, so let's get started and let's see how can we use the beam element stiffness matrix and how can we work with it. So what we are going to do is we're going to talk about Euler-Bernoulli beam elements. And actually, there are many different beam theories. So in our class, we'll just focus on Euler-Bernoulli beam theory. And the idea here is as follows. So let's say that we have a beam. I'm showing here that this is the beam axis. X is the beam axis and Y is the vertical direction. And we can think the center line is actually, when I say center line, is this is the line joining centroid of the cross section. So actually, this x-axis is actually the centroidal axis of the beam. And now I'm showing you a cross section here that is represented by AA. So if you think that if it's a bar element, the cross section only moves in the horizontal direction. Okay. So for the bar element, the cross section is just going to move only in the horizontal direction. But if this element is a beam element, then this cross section actually moves also vertically up and it also rotates. Okay, so this is the meaning of actually the flexure. So this is what it is known as flexure, or this is the property of the beam element. And this is how the beam element is a different element as compared to, let's say, a bar element. Okay, so in this case, you can see that the cross section also have actually axial displacement. So it has both axial displacement, a vertical displacement, and the rotation. In this case, actually, the rotation is measured by the rotation by this angle that the tangent to the central axis makes with respect to the x-axis. And actually, this angle is measured in the anti-clockwise direction. So actually, I'm using the right-hand rule if you wish. So if you think the right-hand rule, the z-axis is outside the screen. And actually, I'm measuring the angle using the right-hand rule, and that is actually in the anti-clockwise direction. But rotation is actually, it turns out, it's not an independent quantity. It depends on the deflection, vertical displacement, or the deflection of the beam. So in this case, the rotation is just the derivative of the displacement. So this is just a derivative of v with respect to x. And you have also learned these things in your previous classes, but this is just a quick recap of the motion of the beam. One thing I want to point out that this is the Euler-Bernoulli beam. So this theory is only applicable to beams, in which case you can think like the depth of the beam is, let's say depth is actually the from top to bottom. Depth of the beam is less than the length of the beam, let's say by the factor of 10. So we can think like Euler-Bernoulli beam theory is applicable to thin beams. If it's a thick beam or a deep beam, then this theory is not applicable. Then there are better theories that we can use. But in our class, we'll just focus on Euler-Bernoulli beam theory. And one of the interesting assumption in this theory is that what happens if you consider a cross section like AA like this. So this is a cross section here, and this is a cross section that is perpendicular to the centroidal axis. So if you think that after deformation, what's happening, this cross section still remains perpendicular to the centroidal axis. And this is a fundamental assumption in a Euler-Bernoulli beam theory. If this cross section does not remain perpendicular to the beam axis after deformation, then it's not a Euler-Bernoulli beam theory. Sometimes we call it that kind of theory in which the angle is not 90 degrees like a Timoshenko beam theory. But we are not going to talk about Timoshenko beam theory in our class. So This is the basic assumptions in the Euler-Bernoulli beam theory, and I'm pretty sure that you have learned these things in other classes. So now we want to move forward and talk about how can we write the equilibrium condition for the beam. First, we will start with the stress and strains in the beam. So we can think that this is a cross-section of the beam, and I'm assuming in this case that the cross-section is symmetric about the z-axis and about the y-axis, okay? So only in our class, we'll focus with sections that have symmetries. So you can think like I-section or a rectangular section. They have nice symmetrics. And so we are just focusing on beam with sections that are symmetric. So if the section is not symmetric, then we have to actually change the beam theory and we have to do some modifications, but we'll not worry about those cases in our classes. So this is the cross section, let's say AA here, and we want to know what is the stress and strain at a point which has coordinates x, y, z. So we want to know the stress and strains at this point. So using the beam theory, we can say that the strain is actually du by dx. This is the axial component of the strain minus y. So y is the distance from the z-axis, or y you can think it's a distance from the, sorry, not the z-axis, x-axis. So this is the distance from the centroid to this point here, okay? And so y is the coordinate of that point. So, and y d square v by dx square, this is the flexural component of the strain. And this is the total strain. So total strain is axial strain minus this thing, this quantity here. That is the flexural component. And finally, once we have the strain, we can calculate the stress. Just multiply the strain by the Young's modulus, E. So this is the stress. And once we know the stress at a particular point, we can actually integrate the stress all over the cross-section to find the axial forces. So axial forces is nothing but just the integration over the whole cross-sectional area A of this stress here. And if we do this exercise, we end up with this expression EA du by dx. So this is the axial force. And for the moment, we just multiply by the stress with the moment arm y bar. And the negative sign is just because of the sign convention here. And if we do the integration over the area, we end up with this expression EI. So you can see that the I automatically comes here. So I is the moment of inertia of the cross section. Okay, so I is y squared dA integration over the cross section of that area, and this is the moment at this cross section. So now what we have done is we have expressed the axial force and the moment in terms of the displacement field. And in this case, the displacement is measured in terms of U field and the V field, okay? So if I go back, there were two variables here. So U is the axial displacement, V is the vertical displacement. Remember, theta is not an independent field. Theta is actually just the derivative of V, okay? So there are two independent fields here. One is the vertical displacement and one is the axial displacement. So moving forward, we want to write now the equilibrium of the beam. And to write the equilibrium, what we are doing is we are taking a small cross section. So this is the small cross section dx here of length dx. And this is a free body diagram, okay? So I'm drawing the shear force, moment, and axial forces here. And V plus dV is the shear force at this side. P plus dP is the axial force at this side. And M plus dM is the moment at this side here. So this is the equilibrium of the small piece. And remember that dV is the incremental change in the shear force V, dm is the incremental change in the moment V, and dP is the incremental change in this force P here. And Q is some vertical traction that is acting. So we are assuming that there is some vertical traction Q that is acting on this section. And if we do the summation of all the forces in x direction is equal to 0, we end up with the equation in the axial direction. And similarly, we can do the summation of all the forces in the y direction is equal to 0. We end up with the shear equilibrium. And actually, now we can do is we can take a point and do the summation of all moments about that point equal to 0. We'll end up with this moment, the third equation here, that is dm by dx is equal to minus vx. This is the equilibrium for the moment. But clearly, the equilibrium for movement actually depends on v. So actually, we can take the derivative of this movement equation and actually combine the shear and movement into one equation. So this is the one equation that we need. So this is d square m by dx square is equal to q. Okay, so you can think that there are fundamentally two equations. One is for axial and one is for moment here. Okay, shear is dependent. So shear is actually dependent on the moment. So shear is not independent. So two are independent. One is axial, one is moment here. And finally, what we want to do is we want to express this in terms of the displacement fields. So what we want to do is we are going to go back here, and we'll take this expression of P and M and substitute this P and M in this equation and this equation here. After we do the substitution, we end up one relationship is for axial. So this is the axial relationship, and the second is for moment or flexure. So you can see that one interesting observation is that the equilibrium condition in the axial direction does not depend on the v field. Similarly, the flexural equilibrium does not depend on the u field. So you can think that the u and v field are independent of each other. So they work independently. So they are not coupled in a sense. Okay. And this is the case for a linear beam theory. If the beam theory was nonlinear, then we will see that these fields are coupled, and then the theory is much more complicated. But for our case in our class, we are just interested in the linear beam theory. And in the linear beam theories, the axial effects and the flexural effects are uncoupled. So you can think that we can study these effects independently, and they don't influence each other. And because of this assumption of that these effects are independent of each other, for a time being, I'm not going to consider the axial effects in a beam, because axial effects is actually, you have already learned. So axial effects is just like if you want to understand the axial effects, you can think this is just a bar element. Okay, so we already know how to deal with the axial effects. So from now onwards, I'm mostly going to focus on the movement or flexural effects. Okay, so this is the equation that we are interested in from now onwards. And later on, actually, we'll combine them, both of them in one element. But to start with, let's keep it simple, and we will just worry about the flexure, or just the important effects that are important for the beam. So let's try to build a beam element stiffness matrix. So here the fundamental assumption is, so we are considering a beam of length L. So you can see that beam can be represented. So I'm just looking from the front of the beam. So I'm not looking at the cross section of the beam. And the cross section, as long as it's some reasonable symmetric cross section, we are good. And the other assumption is the cross section is not changing across the length of the beam, and the properties of the materials are also not changing. So we are assuming that E is not changing. Okay, so the cross section is not changing. It means that the moment of inertia I is not changing, and also E is not changing. These are very important assumptions. Otherwise, our beam, our derivations will not be correct. And so what we are going to do is we are going to represent this beam by the centroidal axis. So instead of drawing this like a thick section, we'll just draw like a thick line here, and then we'll say, okay, this is our beam. And typically, this thick line represents the centroidal axis. So centroidal axis here. And then I want to put the degrees of freedom in the beam element. So at the I end, the degrees of freedom are vertical displacement and a rotation. So there are 2 degrees of freedom. One is VI, and the other is theta I. And the corresponding forces are Py and Mi. Bar indicates they are measured in the local system. Okay, so I will not emphasize on the bar, but it's automatically obvious that we are referring to the local X bar Y bar system, and that's the reason the bar is there. And at the J end, similarly, the degrees of freedom are V sub j and theta sub j, and the corresponding forces are Py and Mj. So Mj is the moment, Py is the vertical force, or the shear. So here Py is the shear, and Mi is the moment here. So you can think that beam element has 4 degrees of freedom: Vi, theta I, Vj, theta j. Okay. So just to give you a physical understanding what these degrees of freedom look like, let me show you the meaning of these degrees of freedom. For example, this is the degree of freedom Vi. So you can see that if the beam is deforming only in the Vi degree of freedom, so let's say that Vi is not equal to 0, Vi is some number, all the other degrees of freedom are 0. So I'm actually showing you how the sections will deform. So you can think that this section just move vertically up by distance Vi. And because we are measuring everything with respect to the central axis, so Vi is actually the displacement of the central axis. So you can see that rather than drawing this kind of figure, we'll just draw the central axis. So red is the central axis before deformation, and blue is the central axis after deformation. So you can see that at the end I, only Vi is non-zero, other degrees of freedom theta is 0, and the end j, both of these degrees of freedom Vj and theta j is 0. So this is how you can think about the Vi degree of freedom. Let's see what is the theta I degree of freedom now. So theta I is actually the rotation at the I end, and you can see that I'm assuming the rotation. I'm using the right hand rule here. Okay, so the counterclockwise direction is the positive direction. So this is the positive direction of theta I, and you can see that the section has rotated in this case, but there is no vertical displacement of the section in this case. Okay, all the other degrees of freedom I'm assuming are 0. So Vj, theta j, and Vi is 0. Only the theta I is present. So rather than drawing this like a thick section, we'll represent this kind of deformation by just theta I, central axis. Okay, so this is the deformation of the central axis. This is red is the undeformed case. And similarly, this is Vj. Again, I'm just representing the central axis. And you can see that in this case, only Vj is non-zero. The other degrees of freedom are 0, just to show you the idea. And this is the last degree of freedom, that is theta j. So you can see that theta j is the rotation at the j end. So the section here is rotating, but there is no vertical displacement at this section here. And at the I end, both the degrees of freedom are 0. And this is how you can visualize it if we just want to draw the central axis. So I'll just represent with central axis because it's simple to draw. So with these 4 degrees of freedom, now what we want to do is we want to find the relationship between the forces and the displacement degrees of freedom. See, I'm using displacement for both the vertical displacement and the rotation. Okay, so I'm using displacement as a general term. So when I say sometimes displacement degrees of freedom, I include both the vertical displacements and the rotation. So what we want to do is we want to see how these four forces. See, I'm also using forces in a generalized sense. So when I say forces, it includes both the vertical force and the moments. So we are interested in how to calculate these forces. What is the relationship between these forces and these displacements here? So forces are Pyi, Mi, Pyj, Mj, and the displacements are Vi, theta I, Vj, theta j. The ordering is very important. Okay, so for the beam element, we will always say the left hand node is I and the right hand node is j, and the degrees of freedom are always ordered as Vi, theta I, Vj, theta j. This is extremely important because that's how accordingly we build the stiffness matrix here. Again, the bar indicates the local axis, but we'll not emphasize in the bar because beam is always in the local axis. But this is important. The bar is there because when we'll take this beam and build a frame element, then we have to do some transformations as we have done for 2D trusses. But for now, we will just work in the local axis because we are always working, a beam element is always horizontal. So we don't have to worry about local and global for now. So let me go back a little bit. So what we want to do is to find this stiffness matrix, what we have to do is we have to solve the differential equation of the beam. And what we are going to do is we're going to start with the differential. This was the differential equation for the flexure. And in this case, you can see that Q is 0. So we have the differential equation is just d square. So it's a fourth order differential equation and not d squared d4v by dx4 is equal to 0. And to solve this differential equation, we have to integrate it 4 times. And once we integrate it 4 times, we'll get the v. But you can see that you will have 4 unknown coefficients, C1s, C1, C2, C3, C4. So this is the relationship of V with respect to X, and C1, C2, C3, C4 are the 4 unknown coefficients. To find these coefficients, actually, you need 4 conditions, and 4 conditions are given by these conditions. So we already know that displacement at I should be VI, rotation at I should be theta I, displacement at J should be Vj, and the rotation at Jn should be theta J. So we have 4 conditions here. So we are going to put these 4 boundary conditions to find these 4 coefficients. And after we put these 4 boundary conditions, we will end up with these coefficients, C1, C2, C3, C4. These are the values. I didn't do that. I'm not doing the algebra on this slide, but I'm just showing you the final result. Okay, algebra I just did by symbolic mathematical software. So we have to solve 4 equations in 4 variables, and then we can get this results here. And after we get this results, we can plug in back, and we have the expression for V. So now we know V. What is the V? Is the displacement field. It's a vertical displacement field. And once we know V, we can also calculate rotation, theta, as a function of x. That's just a derivative of the displacement field, okay? And once we have these, we can actually do all the other calculations that are needed. So in this case, we are interested in actually only the forces at the 2 end I and j. So to get the forces, we first calculate the moment. So moment is EI d square V by dx square. And if we substitute the expression for V, we'll get this relationship here. And the shear force is minus dm by dx. So if we do the derivative of this relationship and with a put a negative sign, this is the relationship we get here. And finally, this m is a function of x. V is also a function of x, but in this case, actually, the shear is constant. It's not changing with x. But these are you can think general functions. Okay. That depends on x, and x is measured from the coordinate 0 in the x is actually at I node. Okay, and finally, to find this pi, mi, pyj, and mj, we just have to evaluate these relationship at the particular locations. So you can see that pyi is equal to minus pyj. And this is just shear at 0. Okay, so we evaluate the shear at 0, and we will get this is the shear at 0, and this is your pyi, and it's equal to minus p by j. And similarly, mi is minus m0. Minus sign is because of the sign convention. I'm not going into the details of sign convention. I hope that you have learned this thing in the previous classes. And for our class, I'm just showing you the derivations here. So if you want to just review your previous class, like the theory of beams, you will be able to recall why there is a negative sign here. For our class, we just want to build a stiffness matrix, and this is what we are interested in. So mi is minus m0, and this is the relationship you will get. And mj is m at L, okay? And we'll get this relationship. And finally, we are going to put these 4 equations in a matrix form. So if we put in a matrix form, this is the matrix form. This is how it looks like. So you can see that we can write py, mi, pyj, mj is equal to a 4x4 matrix times these displacement vector. So it's vi, theta I, vj, theta j. And this matrix is actually the beam element stiffness matrix. So we can, in the compact form, we are writing p bar is equal to k bar times d bar, where k bar is this stiffness matrix, p bar is this element force, and d bar is this element degrees of freedom. So this is the stiffness matrix that we are looking for, and this is what we need when we want to solve beam elements. Okay. So in the next slide, let me give you some of the boundary conditions. What are the boundary conditions that we will actually encounter in our problems? So one kind of boundary condition that we'll encounter, I'm putting a roller here, but it could be just, I can remove the roller because currently we are not interested in the horizontal degrees of freedom. So we are just looking at 2 degrees of freedom, rotation and the vertical displacement. So for this case, we can think like V is fixed because this is not allowed to move in the vertical direction, but the rotation is allowed, okay, because this is kind of a pin connection. So rotation is allowed here. So this is another boundary condition. In the second case, what's happening? This is allowed to actually move in the vertical direction, but the rotation is fixed. Okay. So this is the counterpart of the first case. In the third case, both v and theta are fixed. So this is a fixed end. So both the degrees of freedom are fixed. So these are the three typical boundary conditions we'll find when we are looking into the beam elements, when we are solving our problems. And these should not create any confusion. So I'm just putting the boundary condition. So whenever you see a boundary condition, you know what kind of degrees of freedom are fixed and which are free. In the previous slide, actually, we have not included like member forces. So in general, what can happen? There can be some forces, for example, some distributed traction and some point loads that might act on a beam element. Okay, and to include the effects of these forces, we are actually going to use the principle of superposition that we have used earlier. So what we are going to do is, so what we are interested in, these forces here, Pyi, Mi, Pyj, Mj. And we know that the displacements are given and there are some loads that are acting. So using the principle of superposition, we are going to say that the total forces are equal to the forces due to displacement plus these fixed end forces. Okay, and this is the same idea that we have used for bar elements. So this is nothing new here. So the forces due to displacements are just the stiffness matrix times the displacement vector. And the fixed end forces are some forces that we have to evaluate for a given load pattern. So now the question is, how do we get these fixed end forces? So in our class, what we are going to do is I'm going to give you some typical load patterns. Okay, and people have actually analyzed many cases and created a table of various fixed end forces. So let me show you some of the fixed end forces for various kind of distributions. For example, if we have a beam with uniformly distributed load acting downwards, the load magnitude is Q. Q is the uniformly distributed load, some value. These are the fixed end forces. So at the I end, the moment is QL squared by 12. The shear is QL by 2. So you can think that the total load is Q times L. Half of it goes there and half of it goes here. So QL by 2 here and QL by 2 here. And the moment here is QL squared by 12. How do we actually solve or get these numbers? To get these numbers, what we have to do is we have to just solve the differential equation of the beam. Okay. So in our class, we are not interested in solving differential equations, so we can use this information directly. And in the second case, there is a point load acting at the center. And for this case, you can see that half of the load goes on this side, half of this load goes on this side. This is very obvious. And then the moment is PL by 8, and the moment at the J end is minus PL by 8. And you don't have to remember these values. So whenever some numbers are needed or some kind of load distribution we are using in the class, I will always give this information to you. Let me show you some more crazy distributions here. So this is a case where point load is not acting at the center, but we still have some complicated expressions, but they can be evaluated. There are some algebraic expressions here. And in the second case, there is a concentrated movement. So instead of the load, we can apply actually a concentrated movement. And if there is a concentrated movement that is acting at the distance that is not actually at the center, these are the values of the fixed end forces and the moments. Okay, so you can see that this is the shear here, this is the shear here, and these are the moments at the I and J end. And these are some other interesting distributions. So the distributed load sometimes does not act along the entire length of the beam and is just acting on certain portion of the beam. So for example, in this case, half of the beam. So these are the values. And the second case is the value with the triangular distribution. In this case, you can think that Q is the largest intensity at one of the end, and the load is linearly varying along the length. Okay. And in the last case is like a triangular distribution of load. And these are the fixed end forces for all these cases. Again, I will always provide you this information if it's needed for a particular problem. And actually, there are many other fixed end forces, but I just gave you some of the important ones, and you can find more if it's needed. They're already given in many places, and if you easily Google it, fixed end forces, you can see much more cases. Okay. So let's start with the examples now. How can we use the beam element stiffness matrix to solve some problems? The first problem is a cantilever beam. So this is a very simple beam, but we want to start with a simple case just to see how to solve like simple cases just using the ideas of the stiffness method here. So in this case, what we want to do is there's a beam of length L. The properties are E and I. We are assuming that E and I are not changing along the length of the beam. And Q is the distributed load. And we want to find the unknown displacements and the support reactions. Okay. So the method for solving is exactly the same. So we don't have to change any strategy. So all the ideas you have learned for the truss member or truss structures is still valid here. Okay. So what we have to do is we have to just work with the different stiffness matrix and different degrees of freedom. So let's start with the process. The first step is always we discretize the system and assign the degrees of freedom. So in this case, we just discretize into one element because there is just one element here. And we're going to say that this end is I, this end is J. And then we assign the degrees of freedom. So see, when I assign the degrees of freedom, I'm just going to assign the free degrees of freedom first. So this is the first degree of freedom because this is free. Second is free degree of freedom is the rotation. Third and fourth are the fixed degrees of freedom. So there are two free degrees of freedom, U1 and U2, U3 and U4 are fixed. And with this, the second step is we build the element stiffness matrix. So in this case, we are going to determine what is the element stiffness matrix. So this is the element stiffness matrix. Actually, this is the same matrix that we actually derived earlier. And but we have to put the right degrees of freedom here. So you can think that for the beam element, left node is always I and the right node is always J. So the ordering should be Vi, theta I, Vj, theta J. So Vi is actually 3 degree of freedom. Theta I is 4 degree of freedom. Vj is 1 degree of freedom. And theta J is 2nd degree of freedom. So this is extremely important to get this degrees of freedom right. And finally, we have to also get the fixed end forces. So the fixed end forces with this uniformly distributed load Q, these are the numbers here. QL square by 12, QL by 2, QL by 2, and minus QL square by 12. And so we can put them into a vector here. And the ordering should be the same that we get here, 3, 4, 1, 2. So you can see that this is the first entry is the 3rd degree of freedom. This is the 4th degree of freedom. This is 1st degree of freedom. This is the 2nd degree of freedom. So we have to just put the numbers in the right order. Okay. So if you put the numbers in the right order, the ordering should be 3, 4, 1, 2. It's the same thing, but you have to get the entries right. So make sure that the 1st degree of freedom corresponds to this. The 2nd degree of freedom corresponds to this. 3rd degree of freedom corresponds to U4, and the 4th degree of freedom corresponds to U3. So again, this is the I end and this is the J end. So we actually build the PO vector and the K vector. And now we can go ahead and solve the system. So to solve the system, we have to build P is equal to KU plus P0. So this is the entire system that we can build. And in this case, the degrees of freedom, the free degrees of freedom are actually U1 and U2. So there are only 2 free degrees of freedom. And the supported degrees of freedom are U3 and U4. So U3 and U4 are given to us. They're 0, okay? So what we have to do is we have to just solve the 2 by 2 portion because US is 0. So if we try to solve it, what we have to solve is PF is equal to 0, 0. So you can see that there is no nodal force applied at B. So if I go back, you can see that at the B, there's no nodal force, okay? Q is a member force. So it does not, there's no nodal forces. For example, we could have actually applied some movement at end B or a vertical force at end B, but we have not applied. So P1 and P2 both are 0 in this case, okay? So P1 and P2 are 0. P3 and P4 are the support reactions. And so if we try to solve the system, what's going to happen? We have to solve for just U1 and U2, but make sure that you include POF vector here. So POF is these first two numbers. So we just solve for U1 and U2 in this system. And if we try to solve for U1 and U2, so U1 and U2 are, I'm solving here symbolically using symbolic algebra. So these are the numbers I'll get. So you can see that the first number is the vertical displacement of the B. It's negative. Negative means, okay, the Q is actually vertically downward. So this thing is actually moving. This B is actually moving down. And second is the U2 is the rotation at B. So U2 is actually theta B. And it is also negative. So it means that the section is rotating in the clockwise direction, because anti-clockwise direction is the positive direction of rotation. And this is very obvious, because this is when the beam will deflect, the section at the end B will actually rotate in the clockwise direction. So this completes the analysis of a cantilever beam, but we can actually go ahead and also calculate the support reactions, P3 and P4. If we want to calculate P3 and P4, we have to just back substitute the results. So if you recall the relationship for support reactions, we have PS is KSF UF plus KSS US plus POS. In this case, US is 0 because US is U3, U4. So we don't really need this multiplication here. So what we have to do is we have to just do KSF UF plus POS. So we have POS. So this is, so we do this calculation for P3 and P4. This is KSF UF plus POS. So this is the stiffness matrix. This is this portion here, KSF portion here, times UF plus POS. POS is these last two entries here, okay? So we add these two things together and we get the answer. So this is P3 and P4. So I just put P3 and P4 here. So you can see that P3 is QL and P4 is QL squared by 2. Actually, with quick check, you can see that these are the correct fixed end forces, and we really don't have to do this complex matrix algebra here. You can actually, because this structure is the determinate structure, you can actually find P3 and P4 directly from just looking at the load, okay? But this is just telling you that, okay, the stiffness matrix method works here and it gives you the right answer. So for the simple problem, this is very straightforward, and it just illustrates that, okay, the idea works no matter what. So in the next problem, we are going to increase the difficulty of the problem. So instead of having one beam element, we have two beams. So in this case, we are considering a case I'm calling as a continuous beam. So this is not a statically determinate structure. So this is a statically indeterminate structure. Here you cannot find, for example, the reactions just by equilibrium. It's not possible. And we want to solve the system. So in this case, there is some uniformly distributed load applied on AB portion of the beam that is 2 K fit, and there is a load at the center of the span BC. And the boundary conditions here are, this end A is completely fixed. The B, there is a roller, and the C, there is a roller here. So the B, you can think that the section is not allowed to move up, so it cannot move up and down here. Similarly, at the C, the section is not allowed to move up and down. The properties are given, E and I are given. So E is 29,000 KSI, I is 510 inch for both for the entire section. So they're not changing. This figure is not drawn to scale, so you can see that the 20-foot, this is like a much larger span than 8-foot span, but I'm not drawing this figure to scale in this case here. And what we want to do is we want to find the unknown displacements, support reactions, and member forces. So all the steps are exactly the same. So the first step is to discretize the system and assign the degrees of freedoms. So in this case, what we are going to do is we are going to discretize this structure into two elements, okay? So one is the element AB, or number 1, I'm calling it here. The second is BC, number 2 element here. And then we have to put the degrees of freedom here. So let's think very carefully before putting the degrees of freedom. So we have to figure out what are the free degrees of freedom in the system. So if you think very carefully, there is no free degree of freedom at this end A here. And at the node B, there is only one free degree of freedom, that is a rotation. At the node C, there is only one free degree of freedom, that is a rotation here. Okay, so it's allowed to rotate here, it's allowed to rotate here. And these are the only two free degrees of freedom in the system. So when I assign the degrees of freedom, we are going to assign, I'm going to assign the free degrees of freedom first. So I'm going to say this is the U1 degree of freedom, this rotation at B. Rotation at C is the U2 degree of freedom. And then I'm assigning I can assign in any order. So I'm assigning the vertical degree of freedom at B as U3, and the vertical degree of freedom at C as U4, and then vertical displacement at B as U5, and the rotation at A as U6. So these are the 6 degrees of freedom in the system. Actually, all this degrees of freedom assignment, this is just important if we are doing the hand calculations. If we do the programming in MATLAB, this doesn't matter. We can just do it in any order. But for hand calculation, it's just sometimes convenient to assign the free degrees of freedom first. That's the reason I'm assigning U1 and U2 these free degrees of freedom first, and then the rest are the supported degrees of freedom. And now we can actually go ahead and build the stiffness matrix and the PO vector as needed. The step 2 is determining the element stiffness matrices and the fixed end forces if applicable. So for member AB, this is node I, this is node J. And actually, you can think that the node I is here, node J is here. And this is the stiffness matrix for this member. And so to get the stiffness matrix, we have to do all the calculations, we have to calculate all those coefficients. Let me go back here. So we have to calculate all these numbers here, okay? So you have to make sure that you're using a consistent unit system here. So when I say consistent unit system, in this example, the units I'm using are actually kips and inches. So I have to convert this fit into inches, okay? Else I will not get the correct answers. So for this example, my units are kips and inches. So you can see that if when I use the correct unit, these are the numbers I will get for the stiffness. And for the fixed end forces, because some of the numbers are given in kip fit, so I have to convert into kip inches. If I do the correct algebra and convert these forces, I will get these numbers. So these are the 4 numbers I will get. And you can see that 24, so I should arrange, and this is the I degree of freedom. So my PO vector should be 24, 1152, and 24 minus 1152. So this is the arrangement of the PO vector. And then I have to put the right degrees of freedom. And for the first element, the degrees of freedom, or the member AB, the degrees of freedom are, this is the I node, this is the J node. So the degrees of freedom are VI, theta I. So VI is U5 or 5, theta I is U6, Vj is U3, and theta j is U1. So I have to put 5, 6, 3, 1. 5, 6, 3, 1. So this is very important. And the same ordering, this 5, 6, 3, 1 stays here for the PO. So once you get the ordering for the stiffness, the same orderings go for the PO. So it's important to get the ordering right. And 2 things, get the ordering right and use the consistent unit system. For member BC, there's a point load acting at the center, so we can find the fixed end forces for this case. This is the stiffness entries. Actually, the stiffness entries are, they should be, let me go back. You can see that the length of this beam is different from the length of this beam. So they have the stiffness matrix for these beams are different. Okay, so you have to do the calculation carefully. I'm still using kips and inches as the unit. So this is the stiffness values for this member. And the ordering in this case should be, for beam element, this is the node I, this is the node J. So this is the node I, this is the node J for member BC. This is VI, theta I, Vj, theta j. So it should be 3, 1, 4, 2. So ordering is 3, 1, 4, 2. Vi, theta I, Vj, theta j. And I degree of freedom is always on the left side, and the j degree of freedom is always on the j side, the right side. So this is the ordering we are always going to follow for beam elements. And same thing, we arrange this numbers into the, we are going to just put the Vi. So 6 goes first, and then the movement 144, and then 6, and then minus 144, and the ordering is 3, 1, 4, 2. So we have the stiffness and the PO vector for both the elements. And now what we can do is we can go ahead and assemble this thing into a global system and then solve it. So step number 3 is assemble the global system and solve. For the global system, the system looks like P is equal to Ku plus P0. So we have to build this P0 vector carefully. So this is the P0 vector in this case. So it comes from both member AB and BC. And this is the global stiffness matrix. In this case, as you recall, there are only 2 free degrees of freedom, U1 and U2. So I have partitioned this in this way. So you can think that this block is actually your KFF. This is KFS. This block is KSF, and this is KSS. Okay. When we are solving this system, you can see that PF is P1 and P2, but both, there is no concentrated moment that is applied at the degrees of freedom 1 or degrees of freedom 2. So these are both rotations, but there is no movement applied. So both P1 and P2 are 0. Okay. U3, U4, U5, U6, they're all 0 because there is no support motions here. So this support is fixed. This support cannot move in the vertical direction. This support is also not moving in the vertical direction. So U3, U5, or U3, U4, U5, U6, they're all 0. So you can think that when we solve the system, US is 0. Okay. So what we have to do is, to solve the system, we have to do PF is equal to P1 and P2. They are both 0. Is equal to KFF, UF. So this is KFF. This is UF minus POS. So this is minus of POS, and we have to just solve this system here. Okay. And actually, I just put this negative sign outside. So this is actually this is plus POS, but I just took this negative sign outside this bracket. And we can go ahead and solve for U1 and U2. So this is the solution of U1 and U2. And when we solve for U1 and U2, we can find the U1 and U2. So U1 is actually the rotation at I made a typo here. It should be rotation at B and rotation at C, and these are the numbers here. So I should flip. I'll make the correction on the slides later. So the first is rotation at B, the second is rotation at C, and the units are radians. So whenever you do the algebra, make sure that you have to remember that all the rotations are in radians. Okay, there is none of the rotations are in degrees in this case. So the units of rotations are always radians, and they're very small numbers, and they're like so rotations are always very small numbers if you do the algebra correctly. So this is the solution for unknown displacements, and we can move forward and find the support reactions. So support reactions is actually KSF UF plus KSS US plus POS. So again, US is 0. So we really don't need KSS portion of the matrix. We have to just do the KSF UF plus POS. So this is the to find the support reactions. So in this case, if I go back, support reactions are P3, P4, P5, P6. So this is the KSF portion. So this KSF portion multiplied by UF. This portion multiplied by UF. So this is the same UF that we calculated here. Plus POS. So plus POS are the last 4. So if I go back, these are the last 4 numbers: 36, 24, 1152. So 36, 24, 1152. Add those numbers together with these numbers here, and we'll get the support reactions. And so support reactions are the first 3 are the forces, because if you go back, you can see that P3, P4, and P5 are the forces or the vertical forces. P6 is the movement here. So P3, P4, P5 are, so P3 is this is P4, and P5 is the vertical force here, and P6 is the rotation, it's the moment here. And actually, I finally changed this number from kip inches because all the calculations are in kip inches. So I changed it to kip inches to kip fit just to show you the number in a better way. So this is 108 kip fit. And if you do a quick calculation, quick check, you will see that the entire system is in equilibrium. Okay, so all the vertical forces will cancel the applied loads, and if you take a 1 point and find a moment about that point, you will see that all the system will be under equilibrium with respect to that point. Okay, so it's also under rotational equilibrium, and the system is also under vertical equilibrium. Finally, we want to actually go forward and find the member forces. In this case, the member forces means we want to find the four forces, Pyi, Mi, Pyj, Mj. To find the member forces, what we have to do is we have to take the stiffness matrix multiplied by the displacement vector and add all the fixed end forces if they were there. So actually, we have already done the calculation for the fixed end forces. So we have to just do and we already have the stiffness matrix. So for each element, we have to just do this algebra here to find the member forces. And member forces in this case means calculate these four numbers, Py, My, Pyj, Mj. Okay. So for member AB, these are the, so we take the stiffness matrix, multiply by the displacements here. So you can think that this is the member AB, the displacements you have to put very carefully, and the ordering is actually the same, it's 5, 6, 3, 1. And this is the ordering actually, if you go back, this is the same ordering number here, 5, 6, 3, 1 for member AB. And if you think carefully what's happening, this is member AB, this is the I node, this is the J node. So VI, theta I, so VI is U5, theta I is U6, VJ is U3, and theta J is a U1. So you can, if you do the algebra, actually you will see that U5, U6, U3, they are all 0 because they're supported degrees of freedom. Only U1 is the non-zero degree of freedom here, or theta J is the non-degree of freedom, non-zero degree of freedom. And so you can think that you really don't need the first three columns. So what you need is the last column. So this calculation is actually last column multiplied by U1 plus this vector. So if we do the algebra, these are the numbers we'll get. And again, I put these numbers, I just changed kip inches to kip fit just to show you the numbers in a better way. And these are the fixed end forces I've drawn. So you can see that the first is Pyi, this is Pyi, and this is Mi 108, and this is Pyj, and this is minus 72 is actually Mj. Okay. And if you think very carefully, these loads and the entire beam is in the equilibrium because the span of the beam is 24 feet. So 2 times 24 is actually 48. So 48 kip is acting downwards. And if you add 25.5 and 22.5 is actually 48. So they're canceling each other. So this is the vertical force is under equilibrium. And if I take a point and calculate the moment about that point, you will see that there is also an equilibrium for the moments also. Okay, so you can check that out yourself, but the system is under equilibrium. This beam is under equilibrium. Okay, for member BC, we have to do the similar exercise. This is the stiffness matrix for BC. In this case, BC is this member here. So this is the I node here at this end, J node is at this end. And so stiffness matrix multiplied by Vi, theta I, Vj, theta J. So Vi is actually U3 degree of freedom, that is 0. Theta I is U1 degree of freedom. Vj is U4 degree of freedom, and theta J is U2 degree of freedom. So in this case, you can see that Vj is also 0. Only theta I and theta J are non-zero. So actually, you just need the second and fourth column. So second column multiplied by U1, fourth column multiplied by U2 plus this PO vector. Okay, this PO vector is already we have calculated earlier, so it's exactly the same number, same numbers here. So we just add them together and we get the final member forces. And these member forces are, if I draw it, this is the I end, this is the J end, so it's 15, 72. I have changed this 864 to kip fit. So you divide by 12 to get 72, and then minus 3 and 0. So this is the member forces in this beam member. And actually, you can think very interestingly, the vertical force is actually 12 applied, and if you calculate the fixed end force, this vertical force is here, 15 minus 3 is actually 12. So it's under vertical equilibrium. Again, you can go ahead and check the equilibrium of the movement also, and it will be under equilibrium. And just to show you the flow of forces, you can think like, so these were the two elements. And actually, if you think carefully here, what's happening, so you can see that if I look at the element number BC here, so you can see this is the BC here. So minus 3 is actually the support reaction. And there is no movement applied at this degree of freedom. So this movement was actually 0, or this force was 0 here. And if we look at this this joint here at B, you can see that there is no movement applied here. So 72 actually cancels with 72. Okay, so if we join these pieces together, this 72 is going to cancel with 72 because there is no external movement applied at B. And finally, if you add these two, 22.5 and 15, you'll get the support reactions here. And finally, these two and forces here actually are the support reactions. Okay, so the whole thing actually joined together in the nice way, and the entire thing is under equilibrium. And typically, I don't require you to do these kind of checks, but it's important thing that if you have a problem, it's important that you should do these kind of mental checks to see that if your results are making sense. Okay, so if you have done the algebra correctly, and if you have not done any mistake, your system should be under equilibrium. And this completes the example number 2. And there's one more example I want to go through in this session. And this is the last example for this session. And in this example, actually, I have considered a little more interesting problem. Okay, so now what is happening? It's a continuous beam again. So you can see that now you can see that it has multiple spans. So this is a span AB and BC. At C, I have put a spring here. And there is a span CD. At the end of the span CD, I put a truss member here. So actually what I'm doing is I'm trying to mix like concept of trusses and springs with beams actually. So you can see that how we can use all ideas together that you have learned in one problem. And actually in BC, I put like a triangular distributed load. And at the midspan of this span CD, there is a vertical load of 20 kips that is acting downwards. And at C, I'm also applying a moment that is acting in the clockwise direction, and the moment is actually 6 kip fit. And at D, there is actually a moment that is acting. The moment is actually in the anti-clockwise direction, and the value is 4 kip fit. Okay, and what we want to do is this actually the span is for the AB is the span length is L, for BC the span length is L, and for CD the span length is 2L. Okay, so the length is changing. And again, I have put actually the moment of inertia of the cross section is also changing in different spans. For span AB, the cross section the inertia is I. For the section for span BC, the cross section like the moment of inertia is again I. But for section CD, the moment of inertia is 2I. Okay, so it's twice of this I here, whatever this moment of inertia here is. And with this, we want to solve the problem. And what we want to do is we want to find the unknown displacements, support reactions, and member forces, like solve the complete problem. And what we're going to do here is we're going to assume some certain properties. So these are some numbers that are given. For beam members, we are going to assume that EI is 12 cube times 10 kip fit square. The length is L is 12 fit. So you can think that this is actually 24 fit because this is 2L. For the spring, the stiffness of this spring is 15 EI by L cube. And for the truss member, the EA by L, because EA by L is the measure of the stiffness of the truss member. For the vertical truss member here, the stiffness is 20 EI by L cube. Okay. And we are going to use the units kips and fits here for the entire problem. So we are not going to change into inches because all the units are here in kips and fit. So we don't have to worry about changing the units for this case. So we want to solve this problem. Some important things that you want to remember for these kind of problems is like, for example, I is changing. So you should be, whenever you have problems with I changing, you have to be careful with the when you're working with the element stiffness matrices, because those values will change. And in this case, both I and L are changing. So you have to be extra careful, okay? So make sure that we are using the right values of I and L. For example, because this is, in this case, I is 2I, so we have to use 2 times EI for this beam, okay? And again, with these conditions, we want to solve this problem. So the first thing is we want to discretize this beam structure and solve the problem. And actually, there are many ways to discretize it. So for example, what we can do is we can discretize into like 4 pieces. We can consider as one piece as from A to B, then B to C, then C to the center, and the center to the D. This is one way to discretize it, okay? But if we want to use the minimum number of elements, actually, we can actually discretize into 3 pieces. So one piece will be from A to B, the second will be from B to C, and the third will be from C to D, okay? So we're going to discretize using this way. So this is the discretization of the system. So one beam element is AB, the other is BC, the next is CD, and of course, then this is one spring element, and the spring element is EC, and this is a truss element that is FD, okay? And then we have to assign the degrees of freedom. Again, we are going to assign the free degrees of freedom first. So let's look at the free degrees of freedom. So if I go from every node, so let's look at this node here. So at the node that is at A, we have only one free degree of freedom. That is the vertical motion upward. So vertical motion upward is the free degree of freedom here. Rotation is not free. Rotation is fixed. At the B, the rotation is the free degree of freedom. The vertical motion is fixed. At C, both rotation and vertical motion are free degrees of freedom, okay? At E, you can see that the vertical motion is fixed. So this is the supported degrees of freedom here. And that D, the free degrees of both vertical motion and rotation are free. And at F, the vertical motion is actually a supported degree of freedom. So if I try to write the free degrees of freedom first, U1 is the free degree of freedom. So vertical displacement here is free. Second free degree of freedom is actually the rotation here, so U2. And then U3 and U4 are free. So these are the degrees of freedom at C. And then U5 and U6 are the 2 free degrees of freedom at this node here. So these are the 6 free degrees of freedom. And then I'm writing the supported degrees of freedom. So U7 is the supported degree of freedom. U8 is this rotation here. This is also supported. U9, U10, they're all supported, okay? So 7, 8, 9, 10 are supported. 1 to 6 are actually free. And this is one ordering. I could have chosen a different ordering. So ordering doesn't matter. As long as you order free degrees of freedom, you're fine. This is just my ordering in this case. So you can, ordering in general is arbitrary, okay? So I could have started a different way of ordering. It's fine. But as long as you use the consistent degrees of freedom, you will be okay, okay? So whatever you ordering you choose, as long as you are consistent, self-consistent with whatever you have chosen, you should always be good. After this, what we want to do is we want to build the element stiffness matrices. So you can think that in this case, we have like one beam element AB, second beam element BC, and then beam element CD, and then spring element EC, and then this truss element FD. So actually, we have 5 elements, 3 beam elements, 1 spring elements, and 1 truss element. So we can build all these stiffness matrices and assemble into the global system and solve the problem, okay? One interesting thing is actually, you can see that in this case, this movement here, C, the 6 Kip fit, it goes to the 4th degree of freedom, okay? So you can see that P4 is actually -6 because this movement is acting in the opposite direction to this U4 degree of freedom. So P4 is -6. This distributed load is actually, this contributes to the fixed end forces. And this vertical force here, it also contributes to the fixed end forces. So this directly does not apply to the nodal force. And again, this 4 Kip fit is actually acting in the 6th degree of freedom. So this is actually P6. So P6 is 4, P4 is -6, and P1, P2. So P1 is, there is no vertical force acting here, so P1 is 0. P2 is the moment here, there is no moment acting at B, so P2 is 0. P3 is the vertical force at C, there is no vertical force at C, so P3 is 0. P4 is -6. P5 is 0, there is no vertical force. P6 is 4. And all the others are support reactions, okay? So these are all the PF here in this case. So let's go forward and build the element stiffness matrices and the fixed end forces if required. So for member AB, and now we already know how to build the stiffness coefficients, but I just want to focus on the ordering itself, ordering of the like the degrees of freedom. So for member AB, this is the I node is here, J node is at B, and the degrees of freedom should be VI, theta I. So VI is 1, theta I is 8, VJ is 7, and theta J is 2. So 1, 8, 7, 2. Okay, so this is the ordering. And this is the, if you do the algebra, these are the numbers you will find for the stiffness matrix for member AB. So this is pretty straightforward. Let's try to build the data for member BC. In the member BC, we have this kind of a triangular load distribution. So you can see that if we do the calculation with the given data, we can find these numbers. So these are the 4 numbers you will get if you do the calculation. And the stiffness, actually, the properties are same. So this stiffness, the values of this matrix are actually the same as this values here because I and E and L are same. But let's look at the ordering here. So for member BC, so this is the B and this is the C. I node is here and the J node is here. So you can see that the ordering is VI is U7, theta I is U2. So U7, U2, and VJ is U3, and theta J is U4. So 3 and 4. So 7, 2, 3, and 4. 7, 2, 3, and 4. Okay. And after we build this PO vector, we have to arrange in the same order. So we have to put the 7, 2, 3, and 4. So 7 is this degree of freedom here. 2 is this degree of freedom. 3 is this degree of freedom. And 4 is this degree of freedom. So we have to put in the right order. Okay. So we start with the vertical force here, rotation here, the vertical force, rotation, and or rotation, sorry, the moment here, and then the vertical force 7.2 and the moment 19.2 Kip fit. So I'm not putting the units here, but I'm using a consistent unit system that is Kips and fit for this problem. Okay. Finally, this is the last member or last beam member, CD. In this case, there's a vertical force that is acting at the midspan of this beam member. So we have to calculate the fixed end forces. So these were the fixed end forces. If we do the algebra, these are the numbers we will get. In this case, the stiffness matrix coefficients are different because you can remember that I is different for this member and also the L is different. So but if you do the algebra, these are the numbers you will get. The ordering should be as follows. So this is the C and this is the D. So this is the I node, this is the J node. So again, remember for the beam, the left node is always I, the right node is always J. So this is the I node, this is the J node. And the ordering should be VI is U3, theta I is U4, so 3 and 4. And then VJ is U5, and theta J is U6. So 3, 4, 5, 6. So 3, 4, 5, 6 is the ordering for this case. And this is the same ordering for the PO vector, 3, 4, 5, 6. We have to just put the right numbers here. So this is, we go to the I node and put the vertical force and the movement, vertical force and the movement. Actually, there's some typo in this PO vector. I will make sure to make the correction in this PO vector before uploading this slide here, but I think there's a typo here. I forgot to change this PO vector, okay? But the number should be actually 10, 60, 10 minus 60. So these are the 4 numbers that I should have put in here, but I made a mistake here. Next, what we can do is we can go and calculate the stiffness matrices for the spring member and the truss member. This is very straightforward. And for the spring member, if we do the calculation for KS, the stiffness coefficients 15 EI by L cube actually turns out to be 150 kip per fit. And if you think, you can think like, if you can look in the horizontal fashion, you can think like we are saying that E node is the I node and the C node is the J node. And so what is happening? The ordering should be 9 and 3. So this is the stiffness matrix, 150, 150 minus 150 minus 150. The ordering is 9, 3. So I node is actually E and the J node is C. And this is the stiffness matrix. And similarly for the truss member, EA by L is actually 20 EI by L cube. If you do the algebra, it's actually 200 kip fit. And so again, it's a 2 by 2 stiffness matrix. If we think like a truss member is a bar member, and so it's a bar member in this, like in this direction, this vertical direction. So again, I'm thinking like I node is F and the J node is at D. And so the degrees of freedom are actually 10 and 5. So 10 and 5, okay? So this is how I'm building the stiffness matrix for the spring member and the truss member. And then what I have to do is I have to just put everything together. So let's put everything together in this system. So it's the global stiffness matrix is actually a 10 by 10 stiffness matrix in this case. So you can see that the global stiffness matrix is a 10 by 10 stiffness matrix, and the first 6 degrees of freedom are actually free. So U1, U2, U3, U4, U5, U6. This is UF. These are the unknown degrees of freedom. The rest are all supported, and they're all 0. Okay. So this is all US and they're all 0. So this portion is actually POF and this portion is POS. And this portion is the top right corner is actually KFF. This is KFS. This is KSF and this is KSS. Actually, we don't need KSS portion and KFS portion because whatever the calculation will be, they will be also always get multiplied by US, that is 0. But I've just shown here for completeness. And again, you have to be careful. In this case, actually, PF is not 0. Only P1, P2, P3 are 0. If you think P1 is here, the corresponding force at the 1 degree of freedom, there is no force, so P1 is 0. P2, there is no movement at B, so P2 is 0. P3 is the vertical force at C, there is no vertical force, so P3 is 0. P4 is not 0. And P4 is minus 6 because this load is acting actually in the opposite direction. Similarly, P5 is 0 and P6 is actually 4 because there is a 4 kip fit. Okay. Again, remember that 20 and this 20, the load of 20 is actually a member force. So it creates a fixed end moment. So it's you don't have to worry. We are not taking into account 20 as a nodal force. Okay. Because this does not act at any degrees of freedom. This acts within the member itself. Similarly, all this distributed load Q, like this triangular distributed load, is acting as a member force. It's not acting as a nodal load. And these are the only nodal loads here from P1 to P6. And we have to just solve the system. So this is, we solve exactly in the same way as we solve for trusses. We are going to solve for first for the unknown displacements. So PF is this is equal to KFF UF plus POF here. So this is the first 6 entries from this here. And this is the correct numbers, okay? So I made a mistake somewhere else, but there is no mistake in this portion. So this is all correct. So if we solve this system, we can find U1 to U6. So these are the numbers from U1 to U6. And sometimes I also write U1. So U1 is actually the vertical displacement at A. U2 is the rotation at B. So U2 is the rotation at B. U3 is the vertical displacement at C. U4 is the rotation at C, and U5 is the vertical displacement at D, and U6 is the rotation at D. And I have to be, when I get the answers, I put the units back. So the first is fit, because this is, we know it's a vertical displacement. The second is the rotation, radians, then fit, then radians, then fit, then radians, okay? So you have to be very careful with the unit system that you use, and always write down the correct units when you get your final answers. I sometimes don't write the units everywhere, just because it will clutter the slides if I try to write units at every point, okay? But if you try to use this consistent unit system, you should be able to get the answers correctly. And always remember that there is some unit system that we are working with. Finally, we can go back and calculate the support reactions by back substitution. So in this case, we know that PS is KSF UF K plus KSS US plus POS. Again, we don't need KSS US because US is 0, so this multiplication is not needed. So we have to just do KSF UF plus POS. So this is KSF UF plus POS. So POS, we are just getting the last 4 entries from this global thing. So we're just getting the last 4 entries here, okay? This is actually the last 4 entries are POS, and this will give us P7, P8, P9, P10. So these are the 4 support reactions that we can get. And this will correspond to P7 is the vertical reaction here, P8 is the movement here, and then 9 and 10 are the vertical reactions at E and F. So we can do the algebra and get the support reactions, and these are the numbers that we'll get. So you can see that P7 is in kips. Again, we have to be careful with the units. So the first is actually the vertical reaction, that is kip. P8 is actually the movement, so the unit is kip fit. P9 is actually the vertical reaction, is kips, and the P10 is vertical reaction, the units is kips. So always be consistent with the unit system. And then we can go ahead and find the member forces. So in this case, the calculations are exactly the same that we have done for the previous example. In the member forces means we want to calculate PYI, MI, PYJ, MJ. So this is actually the stiffness matrix times the element displacement vector plus PO vector if that is needed. So for member AB, there is no PO vector because there was no load applied on this member. So we take the stiffness matrix and multiply by the displacement vector for this case. And so if you think carefully, it's the displacement vectors for this case is actually U1, U8, U7, U2. You can go ahead and check it. In this case, U8 and U7 are 0. So actually what you need to do is you have to multiply the first column by U1 and the last column by U2 and just add them together and you'll get this answer. So these are the numbers we'll get here, and I'm showing the member forces in like a free body diagram here. One interesting thing is like there is no vertical forces because there's no member forces acting here. So this thing is under equilibrium clearly, okay? So this is the equilibrium for member AB, or the member forces for member AB. We can do the similar exercise for member BC. We take the stiffness matrix, multiply by the displacements for this member. In this case, the displacements are VI theta I, VJ theta j. They are 7, U7, U2, U3, and U4. Only U7 is 0, and U2, U3, and U4 are non-zero. So we have to put all these 3 displacements. And there's the PO vector. PO vector for this is we have already calculated. So just take the PO vector and add it together. And if we do the algebra, we'll get the answers. So I'm showing the free body diagram here again, or with the fixed and with the member forces here. And you can see that all these loads are under equilibrium. And if you think very carefully what's happening, let's say that the maximum magnitude is here is 4. So if you take the area of this rectangle, that's actually the vertical load acting on the member. So if you remember, the span is actually 12, and the area will be half into 12 times 4. And that actually, if you do the algebra, it should actually turn out to be half of 12 times 4 is actually 24. And 24 is actually equal to 15.07 plus like 8.93. So this sum of these 2 vertical forces is actually 24. So these 2 vertical forces are canceling this this horizontal, like this unify this like triangular distribution of downward acting forces. Okay, so this is actually showing you the system is under equilibrium. At least I'm just showing you a quick equilibrium of vertical forces. You can also do the using your statics, the equilibrium of moments, and it will be under equilibrium. So this is the equilibrium for member BC with the member forces here. And finally, this is the member force in member CD. In this case, the stiffness matrix is different. Just make sure you use the right stiffness matrices for members. And this is the stiffness matrix. And in this case, UI, VI theta A, VJ theta J are actually U7, U2, U3, U4. U7 is 0. There is you have to put the values of U2, U2, U3, U4 that we have calculated and do the algebra. And there is a PO vector here. So there's a PO vector here that we have to add. So we add the PO vector, and if we do the algebra, these are the numbers we will get. Again, I'm putting all these numbers in this free body diagram showing you the member forces. You can see that 11.13 plus 8.87 actually equals to 20. So they are canceling each other. They are nice and everything is fine. And again, I'm not doing the equilibrium for movement, but that if you check it, it should be okay. And for the final two spring members and truss members, we do the algebra as we have done earlier for like these members. So for spring member EC, so I'm thinking this is my EC member. So you can think like this is the I node, this is the J node. So Fi and Fj is actually the forces acting at the E or F9. So you can think this is F9 and F10. So you can think that stiffness matrix times Ui is actually U9, that is 0, and Uj is actually U3. So we substitute the value of U3 and do the calculation. So you can see that these are the two numbers we'll get. So actually, if you think this is the J node here for this member, and Fj is negative 20.06, so it means that the force is acting in the downward direction. And so the force in the spring EC is 20.06. And so the spring is under compression. And this is very obvious because all the loads are acting in the vertical direction. So the spring is under compression. Similarly, we can do the calculation for the truss member FD. So Fi Fj is the stiffness matrix times Ui Uj. So in this case, Ui is actually U10 because this was the I degree of freedom was at the F. So this was the Ui degree of freedom. Uj was U5. And if we put the numbers here, U10 is 0, U5 is, we already calculated U5. If we do the algebra, these are the numbers we will get here. And so we just look at the Fj entry. Fj is actually minus 8.87. And it means that, oh, there's another typo. I'll fix it. So this should be 8.87. So the force in truss member FD is 8.87 compression, okay? So both this spring and this truss is actually under compression. And this ends this last problem. And before I end the session, I want to make some comments. One of the interesting thing is actually I'm calling one member as a spring and one member as a truss, but actually for all technical purposes, they are very similar. So the only difference is I'm using EA by L or KS, but mathematically they are the same. So actually you can take a truss member and replace by a spring. It's perfectly fine. Okay, they both are mathematically, they're both equivalent. So that is one observation. The second observation is, let me go back and tell you some interesting observation here. So if I look at this problem, so what's happening here? So I have applied this moment that is 4 here. So what you can think that this movement is only, so this movement is actually not resisted by this truss member, because truss member can only resist vertical forces. It cannot resist any kind of movement. So this movement is actually only resisted by this beam member, okay? So only this beam member is providing resistance to this this movement. And that is very clear from, if you look at the member forces here for this beam. So you can see that all the force here, so you can see that this 4 kip fit is actually entire force here is actually acting on this beam member, okay? There is no movement in the truss member. So all the movement that we have applied just goes directly to the beam. So none of the movement get transferred to the truss member. But we can still apply the moment at this node because we have a beam member. So what's happening? This entire force is resisted by this beam member CD. Okay, truss is just resisting the vertical motion, so it's not resisting any kind of movement here. So same thing, you will see that this spring member is actually not resisting any movement. It's only resisting any resistance is only coming from the vertical forces. So it's only resisting vertical forces, and you will see that this is also true for this spring actually. Okay, so this is some important observation just to see like the physics of it, and I hope that this example give you a idea of how can we like mix the ideas like springs and beams together, and so on and so forth. And so this is the last example for this session. And in the next class, going forward, what I'm going to do is actually I'm going to discuss another way of solving these kind of problems. Okay, so what we have done in this problem, for example, in this example, is we have done a lot of algebra. So you can see that we have built like stiffness matrices, this PO vectors, and like all these. We have done all the algebra. Like it's just a long exercise, and we built the entire system, and then we solved it. So it takes like there's a lot of algebra involved here. Okay, so you can see that this is all the algebra we have done. But it turns out so this looks like a very algebraic process. Sometimes the process is not giving us any physical intuition, so it just becomes like a tedious algebra. So in the next class, what I'm going to do is I'm going to solve some of these problems using like some physical explanation. Okay, so what I'm going to do is I'm going to put some physical explanation to these stiffness coefficients. So let me go back. For example, this was the stiffness matrix, and actually the way I arrived at these stiffness coefficient was actually I just solved a differential equation. I said, okay, this is the solution from the differential equation, and these are the numbers we get. But I didn't put any physical intuition behind these numbers. Okay, so in the next class, what I'm going to do is I'm going to put some physical intuition behind these numbers, and it turns out that these entities looks very complicated, like some random numbers. Okay, but it turns out that we can easily build the stiffness matrix if we can remember 3 numbers. Okay, so I will call them 3 magic numbers, and as long as we know those 3 numbers, we can actually build this 4x4 stiffness matrix. And it turns out that we don't really need to build the stiffness matrix. In a lot of cases, we can just use those magic numbers to solve the entire problem without building the stiffness matrices. And actually, that's what we are going to do in the next class. But this is a more algebraic or a more comprehensive way of solving the problems. In the next class, we are going to look at more physically intuitive ways of doing these problems. So with this, I would like to end this lecture. And if you have any questions or any concerns, or if you think that some portion was not very clear, you can always contact me by email or just text me, or anything that is convenient to you. One thing I want to make it clear is actually